There is a C operation that implies the deployment of new part of the detector, which typically happens in summer because we need a ship and we need a C operation which stays for 1 month. Then this place becomes quite of a hell with people shouting and running a chicken everywhere. Okay, no, jokes aside, there is a team that controls the power system, there is a team that controls the optical system, there is the data acquisition team, there is a calibration team which operate in turn in this structure in a timeline of about 2-3 months, okay, typically during summer. Then everything is remotized. What it means that now there is a group of typically 2-3 persons in Europe that looks for 1 week at the detector and then they change. We have shifts of check of the detector. And actually what we monitor of the detector, this is a subset of the detector with 30 detection. We measure the pinging activity of a dome. So what is it? A dome, you have seen, has a central logic board, which is nothing more than a computer with an IP address. So it's if you look from the, say, IT manager point of view, the detector is a network of Ethernet nodes. So from here, you reach them, and you see that someone is not responding. In this case, you see floor 0, which is the base, the base of the system is not active in this very moment. Some have not working DOMs. There is one string which is not working and two strings which are not reachable in this moment. Then you measure the rate of optical signals on the dome. And these rates are the basic of the background. So we have potassium-14 water, which produces electrons and then in turn light, because electrons emit Cherenkov radiation. And we know that typically we have a rate of 8 kilohertz per PMT. So this rate is a stable rate that tells us if the detector is working, or its single PMT is working or not, and in general the dome. Okay? So this is another instrument. And then we go for another checklist, check, which is the trigger rate. Okay? We have a level 0 trigger, which is how many signals from potassium-40 we get, typically. And then we have reconstruction of particles, which are another kind of background, which are the muons. I told you that protons interact in the atmosphere, create neutrinos, okay? In general, they create simultaneously one muon and one neutrino back of the envelope, okay? The problem is that the muon is a charged particle, and when it passes into water, it creates directly an electromagnetic, creates directly Cherenkov light. The neutrino has to interact and then create a muon that produces in-turn Cherenkov light. So muons are the ones that you look for, okay, to create your trigger. And the stability of your detector in numbers of events that you detect is monitored constantly to check with the background, okay, with background sources, if everything works properly. Meanwhile, as I told you, the detector, the analysis computer start to detect causality between light signals. This is for a detection unit, which is a string, the Z time plot. Here is time, and here is the height of the detector. If you have potassium-40 only, okay, signals, you see that typically you have scattered, okay, points in the dome. But if you have some, okay, causality,
you can see one here, okay? You start to have a possible track, a possible downgoing track.
Majority of these tracks comes from vertical muons in the atmosphere, okay, which we use as a background.
Some others can have nice patterns like this one. This is probably a Cherenkov horizontal event. These are vertical ones. Okay, this plot together with the rate plot, okay, tells you if, okay, this is actually the muon trigger rate and the muon reconstruction rate, and this is the trigger, the trigger rate of potassium 40. If we compare, for instance, this plot with what we get in Boulogne, we show it. Okey-doke. There it is.
You can see immediately the difference.
Ta-da-da-da. Okay. Where is the mouse?